Hi Margaret, this is a video about the photoelectric effect. I wanted to talk a little bit about light generally, and then I took a couple of problems out of my textbook and we'll see if they make sense to you. The first thing I want to write to you about is how light has a dual nature. This is a little theoretical, but I think it's important to understand. A lot of times when people draw light, they'll draw it like that, like a wavy line. And you know that we talk about the wavelength. The wavelength is the distance between two crests. And then we talk about the frequency. So this is a distance like maybe meters, for example. And the frequency has this weird unit of inverse seconds, or sometimes you see it as hertz. You might see, for example, let's say that the light is moving from left to right. The frequency would be like how many crests pass by, let's say, one point in a second. And so if it takes 1 second for that wave to go by, you would say that the frequency is 7 inverse seconds, or some people like say 7 cycles per second, but you don't really put the cycles in the units. But that's what frequency means. Now the speed of light is 3.00 times 10 to the 8th meters per second. And the speed of light is equal to the wavelength times the frequency. Now the reason that I told you all this again is this part of light's nature is sort of like just called the wave nature. Everything I just told you refers to talking about light as this wavy thing going up and down, up and down, up and down, really, really fast. And you could do some problems with that. But I did mention it has a dual nature. So what do we mean by the fact that it has a dual nature? Well, not only does light have this characteristic of being a wave, sometimes it behaves as if there's particles of energy, particles of light, or you could say particles of energy. That's what Einstein named the photon. So this is the weird thing, and it's kind of mysterious about light. And sometimes it behaves like a wave, and sometimes it behaves like a particle. You have to understand light behaving as a particle to explain what's called the photoelectric effect. This was an experiment that was done at the end of the 1800s, but Einstein explained it in 1905. And he got the Nobel Prize in 1921 for this explanation. Here's the experiment. The experiment is really pretty easy to describe. Imagine you have a piece of metal, something really like shiny, so it's pure metal. What the photoelectric effect is about is that if you have photons of light that are coming in with different wavelengths, only light that has energy greater than something called the threshold energy will cause something interesting to happen. I really shouldn't have done that. I'm going to erase that because it's really the little one that I want to do. So what you would see is certain kinds of light, when put on a piece of metal, nothing happens. And notice the difference. The two words I wrote when I wrote nothing, those were the longer wavelengths. But what I have here is a short wavelength form of light which causes a spark off the metal. It's basically an electrons flying off. Now, what do you remember about short wavelengths from the problems you did earlier today? You probably should remember this equation, that the energy of a photon is equal to Planck's constant times the speed of light divided by the wavelength. So remember, if you have a small wavelength, that corresponds to a large energy. Aha, that makes sense. So what I mean by that is, so you could have, let's say for example, you could plot versus the energy of the photon, and then if I plot the velocity of the ejected electron, what we see here is that nothing will happen until you make the energy of the photon big enough so that, boom, that's the threshold energy. And then after that, if you make light even more energetic, that's going to make the electron fly off faster. Okay? So nothing happens if the light has the energy of the photon too small. All right, so let's take a look at a question here. So this is a question from my textbook. So it talks about the metal cesium. A cesium atom will lose an electron if the light exceeds 3.3 times 10 to the minus 19th joules per atom. What is this wavelength? Okay, and what kind of light is it? Okay, so I actually showed you this equation earlier, E equals hc over lambda, and if you plug those numbers in, you end up getting a wavelength equal to 600 nanometers, or that's 6 times 10 to the minus 9th meters. That happens to be the visible light range. Visible light is between 400 and 700 nanometers is visible. Okay? I really say this, most of the time, you need light in the ultraviolet range. Most of the time you need light in the ultraviolet range because most atoms need more energy than the cesium atom we just talked about. All right, let's look at one more question from my book. This is number 12. That doesn't mean anything to you. But it says, my device requires, so you could say a device requires 6.7 times 10 to the minus 19 joules per atom to remove an electron. Will this work if the light has wavelength equal to 540 nanometers? Okay? So what you need to do is you need to take this energy, so the energy of the photon is 6.7 times 10 to the minus 19th joules, and you need to solve for wavelength. Now, if the wavelength you solve for is greater than 540 nanometers, then the device will work, because the energy of the 540 light is greater than the number you calculated. However, I don't have enough room to write this here, but if the wavelength you calculate is less than 540, it won't. What that means is that if you calculate that this wavelength is less than 540, 540 nanometer light won't be energetic enough to make it work. I hope this helps out. If you're confused about anything, please ask me any questions.